And now I have a switch to install.
I remember.
Okay. Today's lesson is very straightforward. It's only 2 theorems that we are going over. The first one is remainder theorem. Are we all ready?
No. I got it.
Oh, wait, I thought.
Okay, I'm good on my end.
You're good? Okay. So remainder theorem says if I have some polynomial function solved at some x value c, this is equal to the remainder we would get from dividing out x minus c. So remainder theorem says that when I do a division problem, the remainder I get is the same answer I would get if I plugged that x value into my function and solved. F of c equals the remainder from dividing f of x by x minus c. So obviously we're going to start with an example. Okay, in a second we will start with an example. We are set to finish this unit on Thursday and then do an applications day on Friday. Your review is already posted for the final exam on Canvas. So you have until we take the final exam, but we'll talk more about that after the lesson. Just know that it is posted and it's something that you can start working on. Okay, so the example we're going to start with for remainder theorem says if my polynomial f of x is equal to 3x to the 4th minus 2x cubed plus 5x plus 2, use synthetic division to find this function solved at x equals 4. Okay, so the way we're going to do this is we're going to use synthetic division to evaluate. When we use synthetic division for this purpose, we actually call it synthetic substitution, just so you can kind of tell the difference of what we're trying to get as an answer. So when I do synthetic substitution, I first have to evaluate what my x value is that I'm going to be plugging into my chart. That is simply whatever I'm evaluating my polynomial at. So here, since I was taking f of 4, my x value is 4. No, we're not plugging it in. We are using synthetic substitution. So since I'm using synthetic division or substitution, whatever you want to call it, I have to verify that I had no skipped terms in my dividend. Did I have any skipped terms? Yes, which one? The x squared. So I'm going to have to put a 0 in between the -2 and the +5 when I fill in my synthetic division chart. So let's go ahead and fill in that chart. Remember, we just drop down and use our coefficients. So I have 3, -2, 0 for my skipped term, 5, and +2. I build my chart.
Oh, this is the chart again?
Yes. Isn't it fun? And then whatever number I am evaluating at, which here is 4, is the number that goes in that top left-hand corner. And then we just go ahead and do this like normal. So I drop down my first coefficient. Then I take that coefficient, multiply it by the term that I'm plugging in, which is 4. 3 times 4 becomes 12, and that goes under my next coefficient. I add straight down. -2 plus 12 is +10. Then 10 times 4 is 40. 0 plus 40 is 40. 40 times 4 is 160. 5 plus 160 is 165. 165 times 4 is 660. 2 plus 660 is 662. Remember, remainder theorem says whatever remainder I get from the synthetic division process is my polynomial evaluated at that x value. So this means that if I had plugged 4 into f of x for x, I would have gotten the answer 662. So my polynomial evaluated at 4 equals 662. Of course, we don't just blindly expect that this is true. We need to check it to make sure. So what we're going to do next is we're going to check it by taking 4 and substituting it in for all the x's in my polynomial and see if it comes out to be the same answer. So I just like to check it. You don't have to check every single one, but it's good to do a couple of them. So f of 4 equals 3 times 4 to the 4th power minus 2 times 4 to the 3rd power plus 5 times 4 plus 2.
So this is one we.
This is just evaluating to check to make sure that that's the correct answer. This is half of it.
Do you have to check?
On your homework, no, it's not a bad idea to check a couple of them. We're checking here to prove that it works. So on your homework, you're not going to have to check all your problems.
I got a question.
Yes.
Did you do on that?
What do you mean?
Did you put 4 in for 5?
Yeah, I did it right here. 5 times 4.
How about the x squared?
I'll use the plug.
We're plugging it in for x. We just put the x in wherever, the 4 in wherever there was an x, and now I'm solving it.
How about the x
Oh, it's
squared?
got the whole thing.
Yes, the whole thing is going to equal 662 when I'm done, or hopefully. That's the whole point of evaluating a polynomial. So I go ahead and I do all the math for this. And when I do, I get 4 to the 4th times 3 equals 768 minus 4 cubed times 2 is 128. 5 times 4 is 20. And then we have the plus 2 on the end. I go ahead and I put all of that into my calculator, and wouldn't you know it, answer 662, which matches what I got from synthetic substitution. So we have now verified that the remainder theorem is in fact true. So when I do division, the x value that I divided out would equal my remainder when plugged into the function.
We find it false.
Then you messed up.
Ah,
It'll always work. Always, always. There are no restrictions to this.
Wait, so
What is that like B?
Huh?
What is that like B?
That's a check mark I just got. There you go. So we never do just one of these. We are going to do another one, and then we're halfway through our notes. Look at that.
Wow.
Right? I told you it was very straightforward.
now you're gonna change it. Right?
No, I would never.
I don't know, that voice just made it sound like.
Okay. So the next example. If my function g of x equals 4x to the 4th plus 2x cubed plus x squared minus 1. Using synthetic substitution, I would like to find g solved or evaluated at -1.
Is this kind of like that one question on the SAT questions that we asked you about? Like you wouldn't have done like synthetic division.
For evaluating, yes. It's kind of the same. I'd have to go back and look at it again. Okay. So when I am trying to use remainder theorem and doing synthetic substitution, what do I need to identify? The x value that I'll be using. What is that going to be, Miranda? -1. So I always like to write that just so I don't forget. What do I need to check before I set up my chart? There are no skipped terms. Are there any in this problem? Yes.
Yeah.
Yes.
X. I did not have an x here. I went straight from an x squared to a constant. So I need to make sure I put a 0 before that -1 on the end. So I set up my chart. My first coefficient is 4. Then I have 2, Then I have 1, fill in with the 0, and then -1 on the end. I build my chart. And then what number is going to go in that top left corner? -1, because that is the number I'm evaluating at. And then I just go ahead and do my synthetic substitution or synthetic division, whatever you want to call it. Insreisner. Did it work out the same way on your paper? So what does this tell me about g of -1? It's equal to 2. That's exactly what it tells me. Because my remainder after the synthetic division process was 2, and remainder theorem tells me that that's my answer if I would have plugged -1 in. You're welcome to check this on your own. I promise that it works. Okay? Any major questions, concerns, or issues with remainder theorem? Yes. Well, I told you that we're finding the remainder because I was solving a function at an x value. Yes. Yeah. So anytime it says evaluate and you're doing division, I'm looking for that remainder. It'll just say divide or find the quotient, something like that. Questions, concerns, or issues with remainder theorem and using synthetic division to find your remainder, which is your answer. Okay. So our second half is called factor theorem. It is equally as easy.
That's what they all say,
And then they lie.
yeah. But I don't think Mr. M lied on.
You know me, right?
Yeah,
Okay.
for only 2 years.
Okay, so the second here is called factor theorem. This says that if I do division and I get a remainder, and that remainder equals 0, which in other words, we could say that if I solved the function and got an answer of 0, because that's the same thing, then what I divided out is a factor of my original polynomial. So factor theorem says if I do division and I get a remainder of 0, whatever I divided out is a factor and divides evenly from my polynomial. This also applies, since we know remainder theorem, that if I plugged a number into my function and got an answer of 0, whatever I plugged in when turned into a factor is a factor of my polynomial. Okay, because I know that remainder and evaluation go hand in hand now. What? We'll do some examples. It'll make sense with numbers. Or
Yeah, I
about
never
more
understand
sense.
this part.
Yeah. I write it so that once you understand it, you can come back and look at it and it jogs your memory. Or at least I really hope it does. Okay, so we have 4 examples and then we are finished. The first example asks me to determine whether x minus 5 is a factor of the polynomial x cubed minus 7x squared plus 7x plus 15. If it is, then I'd like to find the remaining factors as well. And when I say find the remaining factors, that just means finish factoring whatever we get that's left. So I know in order to determine whether something is a factor or not, the easiest way is by doing division. Since I'm dividing by x minus 5, that's a binomial that is linear, so it doesn't have an exponent on it. So I can use synthetic division, which we're super comfortable with. We've already been doing it a bunch today. So when I'm doing that synthetic division, what do I have to identify?
That's our X.
What is my x? So I simply take that factor or that binomial that is asking me to identify at. I set it equal to 0, and I solve for x, or whatever my variable is. So x minus 5, when set equal to 0, is x equals 5, which means 5 is going to be the number that goes in that top left corner. What else do I have to check?
Check our X.
Make sure all my terms are there. Did I skip any? No. All of my exponents are accounted for, which means I can go ahead and set up my chart. So I have 1, -7, 7, and 15. I know that 5 is going to go in that top left corner. No. And then I just complete my synthetic division process. What was my remainder?
0.
So is x minus 5 a factor? Yes, because it divided out evenly, which means I can now take that original polynomial and I can rewrite it as a product using x minus 5. If x minus 5 divided out evenly and is a factor, what else is going to be a factor, essentially, of this polynomial? How about the answer that I got out of the division process? Right? So I want to go ahead and rewrite this as a polynomial. So when I do, I just apply each of those coefficients to a variable starting on the right at the remainder, constant x squared. So when I do, I get x squared minus 2x minus 3. I like to put the remainder part on there so you can remember that I indeed had nothing left over when I did this division process. So now this quotient and this factor can be written as a product to equal that original polynomial. So I just like to rewrite the polynomial. And then that equals what I divided out times what I had left. So x cubed minus 7x squared plus 7x plus 15 equals the x minus 5 I divided out times the x squared minus 2x minus 3. That was the quotient that I had left after the division process. So if it divides out evenly, I expect you to rewrite it as all of my factors. Then you can just say did not divide out evenly, it's not a factor. That's all we need to do, because I can't find factors if it doesn't come out evenly. Yes?
If it divides out evenly, x minus 5.
So if I get a remainder of 0, it divides out evenly.
Okay.
That's how I know.
Would be example.
A one that doesn't?
Yeah.
We've done a lot of them.
76,000.
Yeah, pretty much anything that gives you like a number there. Any other number other than 0 means it didn't divide out evenly. We're done. Can't do it.
So like the first two.
There's no such thing. 0 is 0.
From like
Yeah, so the first couple, when I got a number out, meant it was not a factor. Right. There was an additional piece to these instructions. It said if it was a factor, then I want to find all remaining factors. Which means, if possible, I need to factor the quadratic that I had left. Is it possible to factor x squared minus 2x minus 3? Rephrased. Are there any numbers that multiply to get -3 but add to get -2? -3 and +1, right? So when I finish factoring it, I have the x minus 5 that I divided out, and then the x minus 3 and x plus 1 that factored from the x squared minus 2x minus 3. If you can finish factoring, you should. You can't always, but majority of time you can. I took this quadratic that was left, and I factored it into x minus 3, x plus 1.
Why is there an X minus 5?
Because that's what I originally divided out. We have to keep it with it. It was a factor. I proved that by the division process. That's not very promising. Okay, so we do have a couple more examples. I hate to say it, but this is one of those things, the more we do it, the easier it gets. So I'm going to give you one that I kind of want you to do on your own, just to see how it works out. And then we will come together, obviously, and go through it. So the one I would like for you to do on your own is show that x minus 2 is a factor of the polynomial x cubed minus 7x squared plus 4x plus 12. If it is, then I want you to find the remaining factors. So on your own, I want you to do everything we just did in the previous example. Move it down so online kids can see it a little better.
No, we ain't gonna do that.
Oh, yeah.
Yes. What are you confused about? No, because it was x minus 2, so I take that and I set it equal to 0, and I solve, and it makes it positive. Reese, did you get this?
Yeah.
Yes. So what does it mean since I got a remainder of 0? That x minus 2 is a factor, right? What do I still have to do then per my instructions? What do I have to do to finish this problem? Paige, what do you think?
I wrote
Quotient, right? Okay, so what did you write for your quotient?
x3 minus x squared minus 5 minus 6.
And then I always like to throw on that remainder of 0, so it's a constant reminder it came out even. So when I did the division process, I got the remainder of 0, which means x minus 2 is a factor. And then as Paige said, the quotient that I had left after the division process is technically another part of my polynomial. So she rewrote it. Again, we work backwards. Remainder, constant, x squared, right? So my quotient was x squared minus 5x minus 6. And then we go ahead and we rewrite the original polynomial we had, and then show that it's equal to these factors that we found, and then that will allow us to finish factoring it. So this original polynomial is equal to the binomial that came out evenly times the quadratic, which was the quotient that I had left. So x minus 2 times x squared minus 5x minus 6. And then I need to think to myself, okay, can I factor x squared minus 5x minus 6? I heard a couple different answers. Okay, what's the one that Brandon said? That's where a lot of us probably went to begin with. What's the issue with that? Okay, I would have to have a plus 6 at the end in order for it to be -3, -2, but that's along the right track, right? We know what he was meaning to do. But because it was -5 and -6, I know that my factors are -6 and +1, which I heard somebody say. So I go ahead and I rewrite all of my factors. Once everything is down to a linear, I'm done. You will not always be able to factor that quadratic, but you should always try. There are some that you just cannot factor, and you'd have to use the quadratic formula to finish solving.
We continue to use the direct formula
Huh?
in our answer
Say that again.
when it gets down to not being able to be
Then we would, yeah, if we were looking for our zeros, yeah. Okay, so I'm actually going to stop after this example because I don't think we need a ton more examples of this. However, I would like to kind of preview you into what we're going to be doing next. So we did all of this factoring, right? Correct? Yeah, we're okay with that. So I did a lot of different things. I learned how to factor it and get it down to its simplest form. The reason we want the simplest form is that eventually I'm going to be finding all of my rational or real zeros for my polynomials. Once it is in this factored form, it's only one extra step to find those zeros. What would I do with these factors to find my zeros? Set them equal to 0 and solve. Which means once I have it in that factored form, I can actually identify what my zeros are.
Can we write this down?
You can. You're not going to be doing this on your homework. I'm just previewing what we're doing next. So once we have it in that factored form, it's really easy to identify what are the zeros or the roots or the solutions to my polynomial. Okay, that is endgame all the time. We're just slowly working baby steps toward it. Okay, this is what we're doing tomorrow. So practice the whole factoring thing today, but realize that this is not the last step. Okay, we are going a little bit farther still. You still have to do it. Your homework is on Canvas. If you have questions, of course, please let me know. Reminder, your SAT questions are due tomorrow. And your final exam review is on Canvas. Your final exam, this is period 5, is next Thursday. They're doing odd periods on Thursday, even periods on Friday. The way that I'm going to run it is that obviously if you're virtual, you have to show